The guide has an ice cube and a problem. The sun is high above the Iranian plateau, the ground is hot enough to shimmer, and his tiny cube is disappearing by the second. There is no socket to plug into, no refrigerator nearby, and certainly no delivery truck carrying bags of ice. But a few steps away stands something that should not belong in this landscape, a huge mud brick dome. Beneath it, hidden in a deep chamber, ice collected during winter could survive far into the scorching summer. No electricity. No compressor. No moving parts. The building itself did the work. This was the Yakhchal, a Persian system for making, harvesting, and storing ice by using cold nights, dry air, shade, earth, and an astonishing amount of patience. It did not defeat the desert. It studied the desert closely enough to make the desert useful. Today, a refrigerator moves heat from inside a box to the room outside, using machinery and a continuous supply of energy. For communities living in the dry interior of Iran, the challenge was completely different. Summers could rise toward 40 degrees Celsius, while winters brought clear, cold nights. Water was precious. Ice was seasonal. If people wanted something cold in July, they first had to capture January and somehow stop it from leaving. The Persian word Yakhchal literally means ice pit. That name is wonderfully honest, because the earliest form was exactly that, a protected hole in the ground where winter ice or compacted snow could be stored. The exact origin of the more elaborate Yakhchal is uncertain. Simple ice storage pits may go back to the first millennium BCE or earlier, but surviving domed structures and detailed descriptions are much more recent. This was not one inventor's sudden idea. It was a system refined across generations. And the system began outside the dome. The guide walks around the structure expecting to find a hidden machine. Instead, he finds a very tall wall and a shallow pool. The wall normally stretched from east to west and stood south of the ice-making area. In the northern hemisphere, that position allowed it to cast a long shadow over the water on its northern side. Some walls reached close to 10 meters in height. Their job was simple: keep sunlight away for as long as possible. Water could arrive through a qanat, an underground channel that carried water from a distant source with gravity alone. At night, workers guided a thin layer of that water into a shallow basin. Thin was important. A deep pool holds a large amount of heat. A shallow sheet exposes more water to the cold air and sky, allowing it to lose heat faster. During the coldest winter nights, the surface froze. The next day or the following night, another layer could be added. Night after night, the ice grew. The dome gets most of the attention today, but this quiet pool was where winter was first turned into a building material. The water was not cooled by one trick. Several small effects worked together. First, the winter air could fall below freezing. Second, the desert was dry, so evaporation removed additional heat from the water. Most surprisingly, the pool also released heat as infrared radiation toward the night sky. Under a clear, dry atmosphere, the effective temperature of that sky can be much colder than the air near the ground. In other words, the water was not only exchanging heat with the air around it, it was also losing energy upward. Modern engineers modeled the ice-making pond at the Yakhchal of Meybod using local weather data. Their simulation suggested that radiation toward the night sky was the dominant cooling mechanism, with evaporation also making an important contribution. Historical descriptions explain that water was added in layers until a substantial sheet of ice formed. Workers broke it into blocks, moved it into storage, and sometimes sprinkled water over the pieces so they froze into a denser mass. This was slow refrigeration. The system did not make ice on demand. It collected a little cold at a time, then saved the result for months. Now the guide finally enters the dome. The floor drops into a deep underground pit. The ice sits at the bottom, far from direct sunlight and surrounded by earth. Cold air naturally settles lower, while the hottest part of the interior remains above the stored ice. Around the chamber are thick walls made from locally available earth and mud brick. At Meybod, researchers estimate that the walls are about 2 meters thick near the base and gradually narrow toward the top. That enormous thickness slows the movement of heat. The material does not instantly become hot when the afternoon sun strikes the outside. Heat takes time to travel through it. This is thermal mass working across seasons. The structure absorbs temperature changes slowly, while the earth around the lower chamber provides a more stable environment than the air above ground. Layers of straw or wicker could separate sections of ice and add insulation. Meltwater drained away instead of pooling around the remaining blocks. Doors stayed closed except when workers needed to add or remove ice. The dome was not a magical freezer. Some explanations focus on air flowing through its upper opening, but modern modeling suggests ventilation cannot explain most of the cooling. The stronger protection came from shade, insulation, thick earthen walls, underground storage, and careful operation. There was no single secret. The secret was that every part helped. So how much ice could this system actually produce? For the roughly 400 square meter pond at Meybod, one engineering simulation estimated about 50 cubic meters of ice during a winter season. That is approximately the volume of 3 million modern ice cubes. This is a model, not a measurement from an ancient worker's notebook. Production would have changed with temperature, humidity, clouds, water supply, and management. Some ice could also come from nearby mountains. Even so, the estimate shows the scale. This was not one family hiding a few blocks under the floor. A Yakhchal could be community infrastructure, filled during winter and opened when the heat returned. In some places, ice houses were operated cooperatively. In others, they were businesses. Ice could be distributed or sold during summer for cooling drinks, preparing desserts, and other everyday uses. Historical accounts even describe celebrations when the ice house was filled or opened. The guide's melting cube was a personal emergency. The Yakhchal turned the same problem into a seasonal public project. For centuries, the Yakhchal remained part of the built landscape of Iran. Then mechanical refrigeration changed the equation. An electric refrigerator needed no winter harvest, large construction, or team of workers. Coal became private and available throughout the year. By the middle of the 20th century, traditional ice houses were rapidly losing their purpose. Many were abandoned or damaged. A survey conducted between 2007 and 2009 identified 129 icehouse sites across Iran's central plateau. Physical remains were still visible at 104 of them, including domed, underground, and walled designs. Only a small portion had been restored. That matters because a ruined Yakhchal can be mistaken for a strange empty dome. The pool may be gone. The shading wall may have collapsed. The channel that once supplied water may no longer be visible. Remove those pieces and the building becomes difficult to understand. But the Yakhchal was never just a dome. It was a network: water, climate, orientation, materials, labor, storage, and timing, all organized around one goal. The guide began with the modern question: how do I keep this ice cold right now? The Yakhchal asks a much larger question: when and where is cold naturally available, and how can we store it until we need it? That idea is still relevant. Modern buildings use thermal mass to reduce indoor temperature swings. Engineers study seasonal energy storage. Designers use shading, earth, nighttime cooling, and local materials to reduce dependence on mechanical air conditioning. The point is not that every city should build a giant mud-brick freezer. A Yakhchal depended on dry air, cold winter nights, water, and people prepared to operate it. Copying the shape without those conditions would miss the lesson. Its real achievement was more intelligent than a single invention. Persian builders connected several ordinary facts. Shadows are cooler. Shallow water loses heat faster. Dry air encourages evaporation. The night sky can pull heat away. Earth changes temperature slowly. Thick walls delay heat. Winter cold can become a summer resource. None of those facts alone creates a refrigerator. Together, they created ice in the desert. By the time the guide leaves, his original cube is gone. But deep beneath the dome, winter is still waiting. And that may be the most surprising part of the Yakhchal. It did not generate cold from nothing. It simply knew when to collect it, where to hide it, and how not to waste it.